0.025 on the right, that was easy. This gives areas to the right. If the area to the left, think about this, if the area to the left is 0.025, what's the area to the right of that marker? Point what?
975.
0.975. How do you get from 0.025 on the left to 0.975 on the right? Are you with me today? I don't know. We just used our table right here, and we said that this value was, what was it again? Like that?
Yeah.
This is a chi-squared right. That's how you write that, chi-squared right. Why is it right? Well, it's on the right. That's why. Now, we're looking for a chi-squared left. That table that you just had out, that I just had out, only gives you areas to the right. So if I look at 0.025, guess what? It's going to give me that again. That would give me the same marker twice and say there's no distance between them when clearly we have a distance between them. True? So you need to be able to identify the area to the right of this. There's 1 under the whole thing. If 0.025 is here, that means there is 1 minus 0.025, which is 0.975. You see where that's coming from? Where's 0.975 fall on your chart? What's it say? Look that up for me. Look up your degrees of freedom for 11. Look up your 0.975 and tell me what it is.
3.816.
3.816? You ever find 3.816? Do you feel okay on finding these two markers? So you'll have two different markers, a chi-squared right and a chi-squared left. We got 3.816, we got 21.92. Here's how you use those things. How you find confidence intervals. What is our symbol that we're trying to estimate? Are we trying to estimate a mu? Are we trying to estimate a p? What are we trying to estimate? Say it again. What are we trying to estimate? Are we trying to estimate a mean? What are we trying to estimate? Population variance. What's the symbol for population variance? That's what we're trying to estimate. We're not a p, we're not a proportion, we're not a mean, we're not talking about mean, we're talking about variance now. Here's how you find your confidence intervals. It's two formulas, one for each side. Remember how we sandwiched our population parameters between a couple bounds? That's still going to happen. Here's what you do. You take your n minus 1 times s squared and your n minus 1 times s squared. Now I want you to see this. These, so far, look a whole lot like that, doesn't it? The problem is, do we have that? We don't. We don't have that. Why? Because you don't know the population variance. If you did, you wouldn't be doing this. Because you know it, right? We're estimating it here now. We're saying we're going to be 95 or 99 or 90% certain it's falling within this range of numbers. You with me on that? So we don't know it. However, the chi-squared gives us an estimate. Do the math on this for me for a second. If you solved for that, you would just interchange those things. You with me? And that's what we're going to do, because that's going to give us an estimate for our variance. It gives us an estimate. A lower estimate, actually it's based on that one, and an upper estimate based on this one. Why am I pointing to the wrong ones, you're thinking? Well, that's a bigger number, right? If I divide by a bigger number, it makes things smaller. Divide by a smaller number, it's bigger. So that's going to give us my two ranges. So interchange those two things, you get an estimate for the population variance. So right here, it's chi-squared right, and here it's chi-squared left. Why does right go here and left go here? Tell me why left goes on this side and right goes on this side. Yeah, I want the bigger number at the right bound, right? If I divided by the smaller number here, that'd be too big. So if I divided by the left one here, this one would be bigger than this one. That's not a good thing. We want them in the correct order. So the right goes here because that'll be bigger. The left goes here because that'll be smaller, making this fraction smaller and this fraction larger. So again, where does this come from? It comes from this, basically. It's giving a lower estimate and an upper estimate for the population standard deviation respectively. That's why we can bind it between those two numbers there. Raise your hand if you feel okay with that formula. Good. Would you like to do one example and see how this thing goes? All right. Oh, by the way, if you want to do standard deviation, if you don't want variance, you want standard deviation, what do you have to do to find standard deviation from your variance? Take a square root of everything. And so this is for variance. And then for standard deviation, well, it'd be sigma. Then you have the square root of all that stuff. You're going to sample 10 appliances. And you're going to read the volts on those things. You see the volt outputs should be pretty, we want these 10 appliances to have the same volt outputs. So say like, I don't know, your hair dryer. Let's do something better than a hair dryer. Maybe your microwave, yeah, your phone charger. See your phone charger. You want every phone charger to put out exactly the same amount of voltage, don't you? I would hope so, because otherwise you go, hey, can I borrow your phone charger? Boom! And your battery explodes. You go, what the hell? That sucks. You just ruined my phone. That worked for my phone. Forget your phone. Right now, we want our phone charger for the same phones to have the same voltage output, don't we? We don't want them to vary very much, because if they vary too much, we're going to end up ruining things. And the same thing with every other appliance. You want them to put up the same number of volts and not have too much spread. So even if the average comes out the same, could you still have the same spread of data? Or, sorry, different spread of data. Do you remember the bank lines at the opening of this class in chapter 3? We had 3, 3, 3. We had like, oh no, it was 7, 7, 7. The 7, 7, 7 was like 1, 3, and I don't know, 17 or whatever it was, 14. And they each had a mean of the same thing, but the spread was completely different. So means aren't the only things that are important. Proportions aren't the only thing that's important. Spread of your data is also pretty important. We want to make sure the spread of the data is not too much. We want a confidence interval to say, hey, the actual spread of our voltage here is within this range. So we're going to be okay. Or, hey, we need to rethink this because this is too much for us. You got it? So that's the idea behind doing a confidence interval and hypothesis testing with standard deviation and with variance. So we have a sample of 10 appliances, and it had a standard deviation of 0.15 volts. We want to construct a 95% confidence interval for sigma and sigma squared, the variance and the standard deviation. We'll do sigma squared first because sigma is how you need that from sigma squared anyway, so we may as well just do that first. Now there's a few things we need to know in order to do this. The first thing we need to know is, what is your S? What is your standard deviation? It has to be given to you. What is it? We also need to know our N. What's our N up here?
10.
Good. From our N, we should be able to find our degrees of freedom. What's our degrees of freedom here?
9.
Great, subtract 1. After that, you need to find two things. So notice we have our S. look up at the board here real quick. We're going to be squaring that s. You follow? Can't forget to square it. If I give you standard deviation, this means variance. You need to square that to get it. We have n, that's great. What's our sigma? What's our sigma? If we knew that, would we be doing this problem?
No.
We wouldn't care. We're trying to estimate, based on the sample, the population of our voltage. That's why we're even doing this. We also need to find the markers, chi-squared right and chi-squared left, for a sample size of 10. So that's going to be changing from our last example where we had a sample size of 12. So every time you do this, you potentially could get a different chi-squared right and chi-squared left. So right now we want to find our chi-squared right, our chi-squared left. Based on our picture, how much area is right here?
0.025.
How are we getting 0.025?
Because your alpha is 0.05.
If our alpha is 0.05, we're splitting that because it's a confidence interval. Confidence intervals have two tails. 0.025 here, that's alpha over 2. 0.025 here, that's alpha over 2. Looks very similar to that. But right now on your table, I want you to look up, find me my chi-squared right and my chi-squared left. So we're looking at our table, degrees of freedom is 9, so we should be on that row. We're using the same columns that we just did though, because we have that same exact picture. So you're going to be looking at 0.025 on the row of 9 degrees of freedom, and then you're going to be looking at 0.975 on the rows of 9 degrees of freedom. And you get two different numbers. What's this chi-squared right one?
19.02.
19 point.
0.023.
Good, and this left one?
2.7.
That's it? 2.700? Sweet. What do we do now? Did you have all this stuff? Just make sure you plug it in right. This is the right one, that's the left one. If you ever get a confidence interval that's backwards, you're like, wait, the bigger number's on the left. You did something wrong. Okay, go back and fix that. So up here we're going to have our n minus 1. That basically is just your degrees of freedom again. Right? N minus 1 is degrees of freedom. So essentially you're plugging in your degrees of freedom here. So we'll have our 9, remember that's degrees of freedom, or n minus 1, times s squared. What is our s again? 0.15. Okay, 0.15. And what are we going to do with that 0.15, folks?
Square.
Do not forget to square that. Over, what's our chi-squared right? Now that's going to be our lower marker, our lower estimate. And over here we're going to have our upper estimate. It's looking the same on the numerator, 0.15 squared. We got that. But here we're going to put our chi-squared left. That's 2.7. How you do this on your calculator without rounding whatsoever, you do this one in your head. That's just your degrees of freedom. You should already have it on your paper. You take your 0.15, you square it, press Enter.